Berkeley, periodic visit to Berkeley. This is a joint quantitative biology institute seminar and physics department colloquium. It's the second of them. And it's really a great pleasure to introduce James, because I have heard him talk many times at the Howard Hughes Medical Institute, and his lectures are always very clear and illuminating and memorable, really. James is the Fred Morgan Kirby Professor and head of the Laboratory of Sensory Neuroscience at Rockefeller University. He obtained his bachelor's degree in biochemical sciences in 1967 at Harvard College, and then he obtained a master's degree the following year in the Department of Neurobiology, also at Harvard. Then in '73, he obtained a PhD in the same department in neurobiology, and the following year, in 1974, he obtained his MD in the Harvard Medical School. James is been many years interested in the process in the biophysics of hearing, really, and has been interested in elucidating both the cellular and molecular mechanisms that underlie the conversion of a mechanical signal, namely sound, into a neural signal through the coupling of sound to specialized architectures in hair cells, which flex and bend and are able to convert the mechanical signal ultimately into the opening of a channel that leads up to the neural signal. As I said, I have been very happy that I have, in the previous times, hear him speak at the Howard Hughes Medical Institute and here at Berkeley, and I really think you are in for a treat. You will see. He has won many awards. I'm not going to mention. I'm only going to mention the fact that he was made a member of the National Academy of Sciences in 1991. Then he became a member of the American Academy of Arts and Sciences in 2002. And I believe last year he was made member of the Philosophical Society. So, James, welcome.
Thank you very much, Carlos. So thank you all for coming. As Carlos has said, I'll be talking about hearing, and I want to start with just a brief statement about what interests us in the subject. And there are really two broad categories of interest. One that's fairly obvious in our society is a clinical interest. About 10% of the population have some hearing deficits, great or small. That's 30 million people. We almost all know people, friends, family, some of us, relatives, who have deteriorating hearing. And that loss of hearing is really quite a problem for people of all ages. For young children who are born with hearing loss, that deprives them of their ordinary avenue for acquiring speech and symbolic communication of all sorts. And that can really retard children's development very appreciably if it isn't attended to promptly. And for the elderly in our society, it's long been the case that progressive hearing loss isolates people from friends and family, the workplace and whatnot, and can be extremely depressing. And for people of any age, one can have total hearing loss overnight from, say, a viral infection. And that can really be devastating to people who've always relied heavily on hearing. Helen Keller famously said that blindness deprives us of our contact with things, but deafness deprives us of our contact with people. And the sort of casual daily interactions that we all take for granted are severed when one loses hearing, particularly when one loses it abruptly. So we and many others have a strong interest in understanding why hearing goes wrong, whether it can be better protected, and particularly whether the hearing problems can be remediated by regeneration of the relevant cells. And I'll tell you about those cells in a moment. For this audience, I think the major motivations for trying to understand a hearing really turn on its remarkable biophysical qualities. And I'll mention three in particular. First of all, we're sensitive to vibrations down to the level of nanometers. the vibrations of the eardrum through a few hundred picometers, and vibrations within the ear of about 300 picometers, or 0.3 of 1 nanometer. So an atomic dimension of vibration can be readily and routinely picked up, even though it's being done by the usual flesh and blood, by lipids, channels, and whatnot. So one wonders how one can achieve this great sensitivity. A second remarkable feature is the frequency range that hearing can encompass. We can hear from 20 hertz to 20 kilohertz, and bats and whales can go up to 100 or even 200 kilohertz, a tenth or 2/10 of a megahertz, which is remarkable for a biological creature. And this is, of course, much, much faster than our other senses. In the case of vision, as you know, if you see images on the order of 20 or 30 times a second, you see that as a continuum. That's how television works. That's how movies work. But in the case of the auditory system, we're somehow able to pick up signals about 1,000 times faster. The third remarkable technical specification is the dynamic range of hearing. We can hear things from 0 decibels, which is the approximate threshold, to 120 decibels, which is about where pain begins. This would be something like being near a jet plane as it takes off on the tarmac. So that's a million-fold range in the amplitude of sound, or a trillion-fold range, 10 to the 12th range in the power of the sound. And there's no other device that I know of that has a 10 to the 12th range of useful information transmission. So that specification is also something that's rather hard to understand. And it turns out that all three of these properties emerge as qualities of the way in which the ear carries out its transduction process. So what I'm going to do is to tell you first about what the ear is doing right now, remind you of what you learned in high school about its structure and how it works, and introduce the hair cells, which are the sensory receptors. And then I'll spend most of the talk on the ear's really remarkable quality, which is that it has an active amplifier built into it. Those remarkable features I mentioned come about because it isn't just a passive transducer, but rather it's a powered transducer that has a very nonlinear system that produces all of these qualities. So to begin, as I said, I want just to show you something about what your ear is doing right now. So this first diagram is a sonogram. At the top, you see a representation of what you would measure if you were just to record my voice coming out, say, of this microphone, a series of syllables over about 2.5 seconds. And below is a representation in a sonogram of the frequency content of those syllables. So some of the syllables, as you can see, are relatively low frequencies, often in stacks of 2 or 3. Others are high frequencies, sometimes rather briefer. And this particular bit is the last stanza of the Dylan Thomas poem, Fern Hill. As I was young and easy, in the mercy of his means, time held me green and dying, though I sang in my chains like the sea. And this bit is, though I sang in my chains like the sea. And you can see that the low frequency pieces are the vowel sounds, though, ang, ains, and whatnot. And the high frequencies are the consonants, sang, chains, see, and what have you. And I show you this just to remind you of the fact that your ears are doing this all the time, every day. In this talk, I'll use something like 60,000 speech sounds or phonemes. And during the day, you hear literally millions of those. And in order to understand what's being said all day, you've got to do this decomposition into different frequencies and then send the information into the brain. And by comparing what frequencies are occurring in what pattern, the brain decides what exact speech sound is being used, and therefore makes speech intelligible. The apparatus that does this is the cochlea. The name cochlos is Greek for snail, for obvious reasons. The snail is this beautiful coil structure that's part of the labyrinth in the inner ear. This also includes 3 semicircular canals you see here, which give us our sensitivity to angular accelerations, rotations of the head or body. And there is a utricle and a saccule that give us our sensitivity to linear accelerations, including the acceleration owing to gravity. Now, to get some idea of how the cochlea works, one can conceptually unroll this device which is about 8 or 9 millimeters in diameter, the size of a chickpea. If unrolled, it's a bit over 1.5 inches in length, 30 millimeters or so. And it consists of a bony shell, the hardest bone in the body, in fact, with 2 liquid-filled compartments separated by an elastic diaphragm that runs down the length. This is called the cochlear partition, and particularly the basilar membrane. This is connected to the eardrum or tympanum through the 3 bones of the middle ear, the malleus, incus, and stapes. So in a very simplistic way, when you listen to a sound, if this were as simple as I've schematized it, sound compressions would push on the eardrum, budge the 3 bones of the middle ear to the right. The last of these, the stapes, would exert, and does exert, a piston-like motion, compressing the liquid in the upper chamber and forcing the basilar membrane down. A rarefaction does just the opposite, moving everything to the left and sucking the basilar membrane up. So if this were isotropic and homogeneous along its length, like a guitar string, plucking it would simply make it oscillate all along its length. But instead what happens is that it's sort of a magical string with different properties in different positions. The top or apical end is tuned to relatively low frequencies. The bottom or base is tuned to relatively high frequencies, and the other frequencies are represented logarithmically in between. So the consequence of this is that if you hear a complex sound like my voice, the different frequency components will be broken down and each represented at a different position. It's sort of a real-time Fourier analysis. The high frequency components are shown here, the middle and the low frequencies, and the relative amplitudes then say how loud each particular sound is. So if we take a more complicated sound, it's going to jiggle the hair cells, the sensory receptors, at different positions along the cochlea. The cells shown here in yellow will respond and send signals down these nerve fibers in blue into the brain. So the brain will just get information about high frequencies from these fibers, middle frequencies, and low frequencies. At any given frequency will excite a particular coterie of hair cells that will excite a particular group of nerve fibers to greater or lesser extents. And that's the information that the brain finally gets. So if we take a bit of that speech I showed you before, the word chains starts with this prominent consonant, which has 2 components, 2 strong lobes that will excite these nerve fibers and these. Then the ains sound has 2 strong components, but rather weaker ones than before, and these will excite these moderate frequency nerve fibers. And finally, the sa at the end will again, but more weakly, excite the high frequency fibers. And the brain has to undo this in order to figure out what's been said. So as Helmholtz first pointed out, this is basically like a piano working in reverse. A piano has a series of nice independent resonators that commingle to make a beautiful sound. The ear undoes that work. It represents each of the frequency components in an independent place along its length and then forwards that information into the brain. So the key player in all of this is the hair cell, the sensory receptor cell. Again, these are what are shown in yellow. There's 16,000 or so in our individual cochleas. And each of those cells is characterized by a hair bundle that gives it its name. So the cell itself is not a nerve cell. It doesn't have an axon or dendrites, but it has this relatively smooth profile. It does make synapses on its base onto these nerve fibers that carry information into the brain. But the organ that gives it its name is the hair bundle, this cluster of little processes sticking out of the top of the cell. In this case, it's about 8 micrometers in height. And it's seen to best advantage by looking down on it from above in the scanning electron microscope. Here you see this beautiful organ pipe sort of structure. The individual processes are of 2 types. Most of them are what are called stereocilia, a name that means a stiff or rigid hair. But as you'll see, they're not true cilia. I'll show you a section in a minute in which you can see that they're really actin-filled processes. The one that is unique is here at the tall edge of the hair bundle. It has this bulbous 1 micrometer swelling. It's called a kinocilium, a name meant to suggest that it's capable of active motion, of kinesis. And it is a true cilium with a 9+2 array of microtubules at its core. There are 2 points that I want to call to your attention. One is that the stereocilia are always in this staircase arrangement. There's always a short side and a tall side to the hair bundle. And you'll see in a minute that that's critical for the way in which it operates. And secondly, the stereocilia don't stand bolt upright, even in a living cell. So this is not a fixation artifact. They always pile up against each other, as you see. And the consequence is that their distal tips are in contact and can move along each other. And that, again, is critical to the way in which the apparatus works. So at the base of each of these stereocilia, there's a taper. Up here, there's some 500 actin microfilaments that you can see clearly. And as these insert into the top of the cell, they're attenuated to a cluster of just 20 or so. And as a consequence, each stereocilium is most flexible or compliant here at its base. And you can see that by taking a living hair bundle, such as this one, and touching it with a probe, such as this glass rod. Two interesting things emerge. First, the stereocilia and the whole hair bundle stay together. And as you'll see later, that's because of various kinds of connections among the processes. And secondly, each of the stereocilia pivots at its base. It does not flex appreciably along its length. So if we take this longest stereocilium here, it starts out quite straight. And when it's deflected, it stays equally straight, pivoting around its basal insertion. Now that pivoting implies that the individual stereocilia must shear or slide with respect to each other, as my arms are doing. And that, in fact, is the fundamental way in which the transduction process operates. The tip of each of the shorter stereocilia is tied to the next longer stereocilium in front of it by this thin structure called the tip link. And there's another one up here, hope you can see them. Each of these is a tetramer of cadherin molecules. The upper 2/3 is a pair of molecules of cadherin 23. The lower 1/3 is a pair of protocadherin 15 molecules. And as you can appreciate, moving the hair bundle back and forth and causing shearing between these stereocilia is going to pull upon or compress this structure. So the basic idea of transduction is shown here. We believe that at the base of each of these tip links, there is one or there more likely are two transduction channels, which are mechanically sensitive channels. Their identity has almost surely been established. They're called rather uninterestingly transmembrane channels, TM1 and TMC1 and TMC2. And the idea is then that when a mechanical force is applied, there's shear between the contiguous stereocilia. That puts tension in the tip links and pops the channels open. This is a very simple mechanism, and it has the virtue of being very fast. There are no chemical intermediates in the picture. There are no second messengers or what have you. So as rapidly as you can move the thing back and forth, and as rapidly as the channels can pop from closed to open, this apparatus will operate. There's also no intrinsic threshold in this system. An arbitrarily small stimulus will produce a slight increase in the open probability, slightly greater current into the stereocilia, and therefore into the cell, and therefore a slight change in the cell's voltage that can be communicated to the brain. So the issue of sensitivity really boils down to just how long the nervous system wants to integrate in order to decide whether something is signal or noise. Now there's an interesting consequence of this direct mode of transduction that I want to illustrate to you with this simple model. This represents a channel. You can see that it can pass cations. It's got a gate that can be open or closed. And attached to the gate is a tip link, which is elastic. So imagine that this arm is a stereocilium and this arm is another stereocilium. What I've been saying is that as the whole hair bundle moves back and forth, the sliding between my two arms causes the channel to alternately open and close. There's an asymmetry in this. In each half cycle, there's some energy taken up by the channel opening, and in the other half cycle, that energy is given back. And that asymmetry has an interesting consequence, that the hair bundle is quite mechanically nonlinear. You can see how this operates if you imagine that you came up and pushed on my arms. If you begin to move my arms to your right, you would elongate the rubber band a certain amount, and you would feel a certain amount of force that depends on that elongation, and it's the same amount if the channel is closed or if the channel is open. But if you begin to push on my arms while the channel is closed and it now opens, the rubber band goes slack until you apply more force. So you'd anticipate that the hair bundle is actually going to get softer over a particular range of positions as the channel gates and then get harder again. And in fact, one can observe this phenomenon by measuring the mechanical forces on individual hair bundles. So the way the experiment is done is shown here. We apply a fine glass fiber to the hair bundle's top. Here we see that bundle from above, the fiber. We image the fiber on a photodiode, and we can measure motions of the bundle and of the fiber's tip with a resolution of considerably better than 1 nanometer and a bandwidth in the order of a few kilohertz. The other thing we can do is by moving the base of the fiber, which is elastic, we can pull the hair bundle, in this case, to your right. And if we know how much the fiber in turn bends, and we know how stiff the fiber is, we can calculate the force that the hair bundle is producing. And I'll make use of that throughout the talk. So if we do this experiment, we see the following. As we displace the hair bundle from its resting position at 0, we see that it's not linear. In fact, a linear relationship would follow Hooke's law, a proportionality of displacement to force, and as you can see, it deviates strongly from that. It turns out that this regime represents the closed channels, this regime represents the open channels, and there's sort of a segue between the two here as the channels go from one state to the other, as I was just portraying with that model. Now, there are several interesting consequences of these. One of them is musicological, and I want to demonstrate that to you. Tortini, who was a great Italian violinist, demonstrated in 1714 that there are nonlinearities produced in our hearing process within our ear that he could readily pick up. What he noticed is when playing a violin or tuning it, that he could play two notes, a higher frequency F2 and a lower one F1. Not surprisingly, he could hear those tones. He could hear harmonics, twice F2, 3 times F1, etc. That's expected. And this depends, of course, on the quality of the violin and so on. But he also could hear sounds that he knew no good violin should be making. So F2 plus or minus F1, twice F2 plus or minus F1, twice F1 plus or minus F2. And in fact, you can understand where these come from if the relationship between displacement and force has this nonlinearity that I just showed you in the yellow curve. That can be approximated by this dotted sort of pink curve, which has a linear term, quadratic term, and a cubic term with different weights to them. And each of those these later terms will produce various kinds of distortions. And those products actually are fairly strong. The theory that I've just shown you would predict that if we play these two primary tones, there should also be power present at all of these different distortion products. And when we actually do this experiment by deflecting a hair bundle mechanically at those two frequencies, we can indeed measure many of those with roughly the correct amplitude. So I'll play a short demonstration of this effect. What I'm going to do is to play first a constant tone, F1, then a second tone, F2, that starts out a bit higher and descends. And then I'll play the exact two same tones simultaneously. Now, the most prominent of these combination tones is twice F1 minus F2. So twice F1, which is not being played, would be up here. And twice F1 minus F2 starts out a small difference and then becomes progressively greater. So we would expect to hear a tone that starts out low and progressively ascends. And that's the way that this demonstration is contrived. There's a constant and a descending tone, but anything you hear ascending is being synthesized in your ear. So here's the first tone, which is pretty boring. F2. Now the same two tones together, and particularly towards the end, as you move through this range, listen for an ascending tone. Some of you hear it? I'll do it one more time. Just, sorry, back. So Tortini and other composers have actually made use of these. Karlheinz Stockhausen Georgi Ligeti, both have composed pieces in which parts of the melody are not played by any instrument, but are in fact synthesized in the ear by use of this effect. The other neat thing about the effect is it's now widely used in pediatric diagnosis, because a normal ear will have this kind of combination tone. So you could take a newborn child who can't talk or otherwise report what he or she is hearing and play two frequencies into the ear, and then use a sensitive microphone to ask whether the appropriate combination tone is emerging. And by that means you can readily assess with a precision of about 99% whether a child's hearing is normal or not. And that's really valuable because in most states it's now legally required to do this while the child is still in the hospital. It used to be that some kids would go home, and particularly if it was the first child, the family might not notice that his or her language was slow to develop. So it might be several years before a hearing loss was noticed. Now it's noticed on day 1 or day 2 before the child leaves the hospital. And of course, this is a very simple and non-invasive test to perform. Okay, so the rest of the talk is really going to focus on this active process that I mentioned. And it turns out that the active process is very closely related to the nonlinearity that I just showed you. The active process has 4 striking manifestations that were noticed through the years in a variety of different animals, in humans, but all kinds of other vertebrate animals as well. The first is amplification. If we look at a particular position along the basilar membrane, the vibrating structure I showed you before, and ask how much it vibrates as a function of a stimulus frequency, each position will vibrate best at one particular frequency called the best frequency or characteristic frequency. If the animal's brain, or rather its head, is deprived of oxygen, for example, by occluding the carotid arteries, one finds that the ear shuts down and the response falls to this blue curve. Now this is a logarithmic scale, so the fall in amplitude is several hundredfold, anywhere up to 1,000-fold. So our ears have a built-in hearing aid, a built-in amplifier that amplifies 100 to 1,000-fold. That apparatus also sharply tunes our hearing. So at any given position, the normal tuning looks like the red curve. As I said, if the animal is dead or if it's deprived of oxygen, the sensitivity falls and the tuning becomes much broader. Even if you enormously amplify the input, this 350 times, you still have this very broad relationship between the frequency and the amplitude. The third characteristic is compressive nonlinearity. If we increase the sound amplitude, first by 10x, then by 100x, we find near the peak that the response grows much more slowly. It grows, in fact, only as the cubed root of the increase in the sound intensity. Away from that peak, however, the system is quite linear, so a 10-fold or 100-fold increase produces a concomitant increase in the response. And the fourth characteristic, which is the really bizarre one, is what's called spontaneous otoacoustic emission. More than 50% of normal human ears in more than 70% of normal human beings will actually emit sound in a quiet room. So if you are put in a sound chamber and an earphone or microphone is put in your ear, there's about a 70% chance that one ear or the other, or both, will emit various sound frequencies. Most people emit something on the order of 4 or 5. The record is something like 34 in a normal hearing woman. So there's nothing pathological about this. In fact, if these emissions do not occur, it's more likely that the ear has been damaged. So there's no utility that we know of to having sound coming out of your ears, but the system is showing the fact that there is a gain control built into it. If you're in a quiet environment, your ear gets progressively more and more sensitive. It turns itself up until finally it's so sensitive that it goes unstable, just like a public address system does if you turn that up too far. There's positive feedback and the system goes unstable. So these are all indications of amplification. This one is particularly striking because there is active emanation of energy from the ear. What we found is that all of these can originate as a consequence of the activity of the hair bundles. The structure I've already showed you that's involved in transducing sound energy into an electrical response is also part and parcel of the amplifier. And I'll show you examples of how these 4 characteristics arise there. First is amplification. So this represents at the top the vibration of an individual hair bundle. And you can see it isn't huge. This is 10 nanometers. So this entire up and down motion is in the range of maybe 40 or 50. When the probe attached to the hair bundle is stationary at its base, the hair bundle bounces around rather irregularly. But as soon as we begin to apply a plus or minus 10 nanometer signal to the base of the probe, the tip of the probe latches on, it's tightly frequency locked to this, and you can see that it's amplifying. This oscillation is almost exactly twice as big as the stimulus that engenders it. So in this case, there's a gain of about twofold, and in fact, with smaller stimuli, you get a much more profound amplification. The second characteristic is frequency tuning. This shows the frequency response of an individual hair bundle. These are from the ear of a frog, and they're tuned to much lower frequencies. In this case, the tuning is sharpest at about, 8 hertz or something of this sort, so much lower than our auditory range. And associated with that peak, there's also a shift in the phase of the system, indicative of a resonance-like phenomenon. Something you might notice if you're a physicist is that the phase can actually lead the stimulus, which is something that a passive system cannot do. So this is another indication that this is an active energy-requiring system. If the hair bundle becomes damaged or if it just gets tired from our interventions, then it becomes quite linear. Both the phase and the intensity are fixed as a function of frequency. Third is compressive nonlinearity. So this is a log-log plot of the displacement of the base of the fiber, which is the input, and of the displacement at the tip, which is the output. Now, if the stimulus is very small, around 1 nanometer, which I remind you is an atomic scale, it's very noisy but vaguely linear. But over most of the range in which we hear, from something like 3 or 4 nanometers to something like 100 nanometers, this has a sub-unity slope, a slope of about 1/3. And that's made more clear by dividing the output by the input to give a sensitivity measure. And you can see the sensitivity has a slope of about -2/3. And I focus on these power law exponents because they're consistent with a particular mathematical object that some of you will be aware of, which is a hopf bifurcation. So a bifurcation is a qualitative change in a system as one continuously and smoothly varies some parameter called the control parameter. So in other words, you turn a knob slowly and the system abruptly leaps between two behaviors. That would be a bifurcation. And an example, again, would be the public address system. If we turn it up gradually, it will get louder and louder, but it will cross a bifurcation and then begin to howl at us at that point. So the bifurcation has a relatively simple formula. There's a complex variable whose time derivative is proportional to a real and an imaginary coefficient times the variable itself. And then there's this funny term that's cubic at the end with a negative sign. And just to detoxify the equation a bit, you know the components of it. If you look just at dz dt is equal to a real coefficient times z, that has solutions that are exponential. If mu is negative, this would decay like radioactive decay. If it's positive, it would grow like population growth. If one were to have only this equation with the imaginary coefficient, the solutions are sine and cosine waves. And if one combines those two, one gets an exponentially damped sinusoid or an exponentially growing sinusoid. All that this last term does is to intervene when this grows too large. What will happen as a result of this negative sign is that this will grow to a certain size and then continue to oscillate at a constant frequency forever. It's a limit cycle oscillation. Now, the reason that I call your attention to this is that you can add a forcing, an input stimulus to this equation, and actually analytically show that the response is proportional to the force to the 1/3 power, or the sensitivity, which is the response divided by the forcing, is proportional to the forcing to the -2/3 power. So these are exactly the behaviors that I showed you, and those same behaviors are found in the mammalian cochlea and other experiments. So this is at least consistent with the hopf bifurcation, and we'll come back to evidence for this later on in the talk. So here's the fourth and final quality of the active process, which is spontaneous oscillation. Individual hair bundles, as you see here, can oscillate well above the amplitude expected for thermal motion. Some of them, like this one, oscillate relatively quickly and regularly. This one has a lower amplitude and is more irregular. If you record from many of them with a probe, you can see that different hair bundles have different properties. Some are relatively fast, relatively metronomic. Some are slow and show these striking limit cycle type of oscillations. Some are just very ratty looking. We believe that these underlie the spontaneous otoacoustic emissions, of which I'll now play you an example in the human. So the high-pitched whine you can feel are these two oscillations. You can feel heartbeat, you can feel the stomach gurgling, the clothing. The hissing is the background noise pulling the microphone. And there are these other weaker emissions as well. I chose this one just because it's very typical with something like 4 or 5 prominent. So if we record from an hair bundle that is showing strong amplificatory behavior, we get a surprise, which is that it shows a region of negative stiffness. That is, the relationship of displacement and force has a region of the opposite slope to what you would anticipate. Now, negative stiffness is something you don't see very often. We didn't know what it was when we found it. So here's a cartoon giving you some idea of it. If the hair bundle is sitting at rest, as you see here, the fiber attached to it is straight. If you move the fiber well in the positive direction, it will pull the hair bundle in the same direction. And the fiber, being elastic, will bend back in so doing. But what's striking is if you move the base of the fiber a small distance in the positive direction, the hair bundle moves farther in the same direction. So it's as if I pushed on this table, and instead of the table pushing back, it pulled me in the positive direction. It says that there's some energy stored in the table or in the hair bundle that can accentuate a motion. And it turns out that that activity is associated with the gating of the transduction channels. And here's an experiment to show that. Here's a hair bundle oscillating spontaneously, as you've seen before. And at this point, we turn on a jet of gentamicin coming out of a pipette. Gentamicin blocks the transduction channels. While it's present, the oscillation is suppressed. And then when the drug is turned off and washes away, the oscillation recurs. Now, if at each of these 3 different epochs, we made measurements of the relationship of the displacement and force, we find that either before the drug is present, or again in blue after it's present, there is this region of negative slope sensitivity, slope stiffness. But while the drug is present, the system exactly obeys Hooke's law. It's totally linear. So somehow the ability of the channel to open and close is essential for the nonlinearity to occur. And a notion of what could be happening is shown here. The idea is that you have transduction channels, shown here in blue, that have a red gate that can open and close and is attached to this elastic structure, the gating spring. This could be the tip link, for example. If we have 3 such channels in parallel with each other and begin to apply a force to it, that force will be evenly divided among the 3 closed channels. But as soon as one channel pops open, this spring will relax a bit, meaning the other 2 springs have to assume a larger load. So this closed channel will now have more force on it, and it may also pop open. So now if 2 channels have opened, the remaining closed channel will bear still more force until it pops open as well. So the system is bistable. It's perfectly happy if the force is small and all the channels are closed, and that corresponds to this limit of the curve. It's equally happy if there's a strong force that pops all of the channels open, which corresponds to this limit of the curve. But in between, there's an instability. As you begin to pull on the system, there's an avalanche with all the other channels popping open. Or again, as you begin to relax it, there's an avalanche going the other way that causes all the channels to reclose. The system is not stable between these 2 points. Now, the idea that these channels are truly in parallel with each other is questionable, because I've shown you that the channels sit on different stereocilia, and you might suppose that they're quite independent of each other. And this is amplified if you look at a micrograph. This shows about 60 stereocilia, the 1 kinocilium at the tall edge. Force is applied to this kinocilium, which applies it to these adjacent 5 stereocilia, but then must propagate across the hair bundle. And you might suppose that the signal would get progressively attenuated as it does so, and that the channels wouldn't truly be in parallel with each other. And here's a schematic of that. You can imagine that if the stereocilia are really in series with each other, putting a force here will open this channel perhaps by pulling on that tip link, but less probably open in that one, less as you move across. And the model I showed you really relies on the fact that the stereocilia work in parallel so that a force applied here is evenly distributed among all of them. And in fact, we've tested that idea by looking at how a hair bundle moves under Brownian motion. If the stereocilia are in series and can separate from each other, we would expect that Brownian motion would bang on the bundle and cause the stereocilia to evince breathing motion, separation from each other along their length. Whereas if they always remain in parallel with each other, the stereocilia would remain in contact and the bundle would always move as a unit with only a single degree of freedom. We tested that by making a micro-interferometer that had two beams, a red beam and a green beam, both put at different positions, such as the tip of one stereocilium. And each of those beams had two orthogonally polarized components that constitute a tiny interferometer. So we could make sub-nanometer motions here and here simultaneously. Then analyze the response by looking at the cross-correlation between the movement of the two beams. So if both beams are positioned together, the cross-correlation, which is shown in yellow, is pretty much identical to the autocorrelation of the red signal with itself, which is the dotted red curve. But now if we do the interesting experiment, we move one beam to the opposite side of the bundle and cross-correlate those two positions, and we find that the cross-correlation is pretty much as good as it was before. So whenever the hair bundle jerks to the right at the tall edge, the short edge moves as well. When it moves to the left, similarly. If we instead move one of the beams over to another hair bundle altogether, we see no correlation between the two. As I showed you in the movie, they're all operating independently of each other. So what is holding the bundle together? There's several possibilities. One of them that I've shown you already is that there are linkages of various sorts between the stereocilia, and those linkages could pull the hair bundle, pull the stereocilia together. The surfaces of the stereocilia are electrically charged, and that could hold them together. The stereocilia are inserted into an actin web called the cuticular plate, which is warped and could force them together. And finally, there might be hydrodynamic forces that hold the stereocilia together. We've tested all of these. They all have quantifiable effects, but the dominant one turns out, surprisingly to me anyway, to be the hydrodynamic one. And we approach this a number of ways, but perhaps the most useful to show you is simply by using finite element analysis, looking at 200,000 nodes in this system, so individual stereocilia and the surrounding liquid, and then applying the Navier-Stokes equation for incompressible liquids. And when we did that, what we found is shown in this next movie. Here we have different frequencies being applied to the kinocilium and to the adjacent 5 stereocilia. So at very, very low frequencies, just those stereocilia move back and forth. But as we begin to approach the auditory range, hydrodynamic coupling spreads across the array. So you can now see that the whole thing as a unit. These represent various volume elements of the water around. So what is happening is shown here. If you take 2 stereocilia, these 2 red ones in the hair bundle, and then displace the hair bundle, there are really 2 options that the stereocilia have. One is that they could separate from each other. The problem with doing that is that separation of the narrow space between the 2 requires the sucking of water or of saline solution into this tiny, tiny nanometer scale volume. And that turns out to be energetically very inefficient as a result of the very high drag associated with it, which is 2,000 of these particular units. The alternative is that the stereocilia stay in contact with each other and shear longitudinally. If that happens, there's no need to move liquid in or out of the narrow space. The liquid simply moves longitudinally as well. And as a consequence, this is more favorable by about a factor of 2,000. So this mode is much preferred, and the stereocilia are held together by hydrodynamics, even at very high frequencies, up to at least 10 kilohertz and probably above that. Okay, so we have a machine that has 1 degree of freedom. It moves as a unit. It has a stable fixed point here. It has a stable fixed point here, but an unstable fixed point in between. And throughout the red regime, the hair bundle cannot reside stably unless we apply a force to it externally. So the system is bistable. It wants to jump between those two positions, whether driven by noise, thermal noise, or driven by some sort of a mechanical stimulus. In fact, that's what seems to be happening. There is a system that uses a power source to harness this instability and to turn it into an oscillator or an amplifier. The power source is associated with adaptation. If we take a hair bundle and apply a constant force to it, we see transduction channels open and a current surges into the cell. But within about a millisecond, most of the current turns off, and then there's a slower relaxation over about 20 milliseconds as additional channels shut. And associated with those two events are movements of the hair bundle. This rapid adaptation is associated with the jerking of the hair bundle back in the opposite the direction of the force. And then this slow relaxation is associated with a slow relaxation of the hair bundle in the same direction. So the latter in particular is striking. It's as if I push again on this table, and instead of staying put, the table gradually sags and I move farther in the same direction. It's as though the table is getting softer with time so that a constant force causes a greater displacement. And in fact, we've done extensive work showing the basis of that, and it involves a resetting of the tension in the tip link. So here's the hair bundle at rest. There's a certain tension in each tip link, and the channels are largely closed. We apply a force, the hair bundle moves to the right, and the shearing between the stereocilia pops the channels open. But what we now think it occurs is that the upper insertion of each of these tip links slides down. And as it slides down, it reduces the tension in the tip links with two consequences. First, the initially large transduction current asymptotically fades to a plateau. And secondly, the initially small displacement increases with the same exponential time course. So this is so-called slow adaptation. And as you can imagine, if you move the hair bundle the other way, the tops of the tip links must climb up. And that's actually actively mediated by myosin molecules. So myosin is, of course, the protein that we use to contract our muscles. This is a different kind of myosin called myosin 1C that's found at the stereociliary tips. And it moves up and down, adjusting the tension in the tip links and giving rise to that slow adaptation. The myosin is also an energy source that can pump the amplifier. The fast component of adaptation is something we still do not wholly understand. The fast component is mediated by calcium entry. So again, we open the transduction channels, calcium flows in, shown in pink. It binds to something associated with the channels and recloses the individual channels. Now, as you can appreciate, if you close the channels from this state to this state, the tip links will be extended. That produces a force that pulls the hair bundle back in the negative direction. So you have a system that is pushed to the right, but then jerks back to the left. And in fact, that can produce a cyclic reaction mechanism shown here. Here's the hair bundle subjected first to positive force, say a sinusoidal force, and then to negative force in each cycle, going round and round. During this phase channel open, calcium runs in, but the calcium now binds and produces a force in the opposite direction that augments the force produced by stimulus. So in each cycle, the calcium is acting like a little turbine that's adding energy to the oscillation. And in fact, if you model this system, you can show that this makes a very nice amplifier. The model says that the hair bundle's velocity, the derivative of its position, is proportional to certain drag coefficients, to a nonlinearity reflecting that cubic term that I showed you previously, and just to the linear elasticity of the hair bundle and the associated fiber that's attached to it. And there's an adaptation time constant associated with the behavior of the myosin molecules. If you actually test that, what you find is that a stimulus force applied to a passive hair bundle would produce a tiny response. If the channels are allowed to gate, you get only a slightly larger response. But if this calcium feedback is engaged, There's now amplification of more than 100-fold, building up over a few cycles and fading away over a few cycles, just the sort of behavior we see of the amplifier. Moreover, it's sharply tuned. So for a particular set of parameter values, there's one particular frequency for which it's most responsive, and it shows a compressive nonlinearity. As the stimulus gets larger and larger and larger, the gain of the system gets smaller and smaller until you approach linearity. So all of the properties of the active process seem to come out of that simple sort of a model. And finally, if you adjust the control parameter in the model, the same input will get progressively larger and larger and larger responses until you cross the hopf bifurcation. Now the system begins to oscillate spontaneously and could produce the spontaneous emissions that come out of the ear. So the last thing I want to talk about is recent tests of this sort of model that also bear on the issue of the different loads that hair bundles confront. There are hair bundles in different contexts, such as those on the surface of animals like fish, the zebrafish in particular here. Here the hair bundles are sticking out into the water, and they're simply measuring the fish's motion or water motion around the hair bundle. In our vestibular apparatus, such as the frog sacculus, the hair cells are in contact with a gelatinous structure that's loaded by calcium carbonate crystals. It's just an inertial mass. So if you move your head, tilt from side to side, that inertial mass lags behind the rest of the organ, and that pulls on the hair bundles and gives you a sensitivity to linear acceleration. And finally, in the cochlea, the hair bundles that stick out, in this case, are confronted with this rather elaborate gelatinous structure called the tectorial membrane. As the basilar membrane bounces up and down, there's a back and forth shearing motion that deflects these hair bundles. And the point of the slide is that different hair bundles confront very different loads. This one confronts a mostly gelatinous load and water. This one confronts a highly inertial load. This one confronts some combination of inertia and elasticity. So we might anticipate that these different hair cells will operate in different regimes depending upon the nature of the load applied. Now, in the equation I showed you before, we can actually control experimentally what elastic stiffness the hair bundle meets with and what external force is applied to it. So we can test this idea by actually doing experiments in which we ask what is the behavior of the hair bundle when we change those variables. And this is just a reminder of something called a state diagram. A state diagram says that something like water can exist in different states depending on various control parameters, in this case, temperature and pressure. So here we have vapor, here we have liquid, and finally here we have different flavors of ice. And in a similar way, we would predict that a hair bundle has different states. If we control the elastic load applied to it and the offset force, the steady force applied to it, we get this fish-like shape. Within the fish, we anticipate spontaneous oscillation of the hair bundle. And as we move towards the right side, the frequency should increase. As we move towards the left side, the amplitude of oscillation should increase. This regime is bounded by hopf bifurcations, such as the ones I've described for you previously. Over here, we have saddle node bifurcations. And the rest of the space, the hair bundle is either monostable, it sits in one position, or it's potentially bistable, but not oscillatory. It can be knocked by noise between two states. So to test this idea, we devised something of a feedback system, which we call a mechanical load clamp. Basically, we again measure the position of the hair bundle. We use a computer to compare that position with a command that's being exerted. So this computer says, I want you to be at a certain position corresponding to a certain stiffness or corresponding to a certain force applied. And we can control the gain of the system at the same time. We feed back the resultant signal through a piezoelectric actuator that moves the hair bundle accordingly. And by so doing, we can test the hair bundle in a given set of parameters of elastic load and constant force and get these sort of state diagrams. So this is one and the same hair bundle in records a few seconds apart. And as we move from this position to this position to this position to this, we can see initially large spontaneous oscillations, then progressively smaller ones, and finally suppression of the oscillation altogether. And as we anticipate, and as the color code shows, as we move in this direction, we have a decrease in the amplitude. As we move in this direction, we have an increase in the frequency of the response. This is vaguely fish-shaped. This is just the confirmation. So we are, and I should say the black regions around are quiescent. So we are seeing, as we anticipate, a regime in which there's some sort of a bifurcation, and we believe we have a lot of evidence that this is a hopf bifurcation between the oscillatory and the quiescent regime. If in these different regimes we measure the responsiveness, in this case, the response amplitude during stimulation, we find that being close to the boundary, to the hopf bifurcation, is ideal. So when we're just adjacent to the bifurcation, not quite across it, we get the largest response, we get the sharpest tuning, the highest Q. And as we move farther and farther into the quiescent regime, in other words, as we move farther and farther out in this direction, we get progressively weaker responses and a progressively lower Q. So it really does seem to be that at that boundary, the hopf bifurcation, the system is ideal. Overall, the virtues of the hopf bifurcation in this context are shown here. The hopf bifurcation explains all the qualities of the active process I told you about at the outset, the amplification, tuning, and compressive nonlinearity, as well as this epiphenomenon of spontaneous otoacoustic emission. The hopf bifurcation is the simplest bifurcation that's relevant to this, in that it occurs in just 2 dimensions, which is the lowest dimensionality in which you can get oscillations and the like. It's codimension 1, so tweaking just a single parameter can take you across the bifurcation. It's a local bifurcation that occurs about fixed points. A system with a hopf bifurcation can be easily entrained to a sinusoidal stimulus, which is a virtue if you're listening to sounds, and it has frequency constancy. As you move across the bifurcation, the frequency to which the system is tuned stays more or less constant, which is useful because as the system is turned up and down, you don't want it to change in its pitch or its sensitivity to sound as well. And finally, it also produces the combination tones that I showed you in the demonstration. So what we're working on right now is how the system might adjust itself. For example, we might anticipate that in a loud environment, you don't need sensitivity, so you move away from the bifurcation off in this direction. As the system becomes quieter, you move towards it. For optimum sensitivity, you might move to this point just around the bifurcation, where we've shown the sensitivity to be greatest. And finally, in an ultra-quiet environment like a sound chamber, you may move well into the fish to a point where you'll get spontaneous otoacoustic emissions of the sort that I showed you. So the bottom line of all of this is that these elegant structures, the hair bundles, are not just mechanotransducers that pick up the sound that is applied to them. These are also the soul of this amplifier, of this active process. They account for the amplification, for the sharp frequency tuning, for the compressive nonlinearity, as well as for the various epiphenomena that I told you. And this is, as far as we can tell, a unique set of sensory processes that are not found in any of our other senses. We don't know of any others that are powered, that actually use the energy from ATP to enhance the signal in these various ways. So at this point, I'll be happy to stop, and I would be very happy indeed to take any questions. Thank you. Right. So the question is why is it that if the hair bundles are independent of each other, why do we have different frequencies of emission from the cochlea? And the answer, again, turns on the fact that, say, in mammalian cochlea, you have about 3 turns, and those 3 turns correspond to different frequencies. So these are high frequencies. The tip corresponds to low frequencies. And what was supposed to be happening is that oscillation, owing to active hair bundle motions and other things, are occurring at different positions. So if the hair bundles right here are particularly energetic, we would get a middle C or something coming out. Here would be C above middle C, 2 Cs octaves up, 2 Cs farther down, and so on. So Just a subset are actively moving. Now, there's some other animals. If you look at a lizard, like a gecko, we know not what geckos are thinking, but geckos have these beautiful combs of emission like that. So in this case, it seems that most of the hair cells are active, and there's a good deal of theory that's going into how these are organized. It's an organizational principle in which you have coteries of cells. In this case, there are 170 structures, they're called sallets or salles, that are conjoining the hair cells, and somehow these get divided up into something like 5 or 6 groups that oscillate together. And by doing Arnold tongues and whatever, one can get at what is behind this synchronization between them. Right. So the phenomenon is, as you said, is tinnitus. And I should say at the outset, people sometimes say tinnitus. Itis means in medicine an inflammation or possibly an infection. It's tinnitus, which is meant to imply not an infection, but in fact just ringing. It's a bell-like or tonal sound in the ear. And it comes from several different things. One thing that can do it is the active process that I told you. There are occasional ears that go unstable and stay unstable. Some even stay unstable in normal environments. So there are people who have an emission that can be heard, a meter away in a suitable, ordinary, quiet room. So somehow their active process gets stuck on, turned up to 11, and you can't turn it back down. Heaven knows why this is the case. People who have that usually don't notice it, because it's just like the sound, for example, in this room from the air conditioner. You haven't noticed it, right? You tune it out in your brainstem as soon as you come into a room. So people who have this don't notice it. But if you move that emission a little bit by changing the pressure in the ear, just by putting your thumb in the ear and pushing, the mechanics changes slightly, the pitch changes slightly. People then hear it for a few seconds until it fades away again. That kind of so-called objective tinnitus that can actually be measured is relatively rare. Most tinnitus, particularly as we age, is analogous to phantom limb pain. So as most of you know, if you have an amputation, you often can feel the missing limb. And that comes about because of the fact that the input from the somatic receptors here that goes to this portion of the brain is turned off, and the brain basically is turning its gain up. It becomes more sensitive until it begins presumably to oscillate spontaneously and produces a fictive sense of motion, of touching, of pain, of burning, or whatever. And the same thing seems to happen with most tinnitus. One loses a particular range of frequencies. The auditory cortex on the contralateral side or both sides is deprived of its normal input, and it then becomes spontaneously active and begins to make up sounds that are not actually there. And that tinnitus tends to occur as we lose particular frequencies. Our frequency range originally is sort of a broad curve like that. We tend to lose higher frequencies first. So with age, things get pared down. I'm down from 20 kilohertz to 12 kilohertz, which doesn't yet have much of an effect, but a few more kilohertz and I'll start suffering. I won't be able to hear my wife or other relatively high-pitched voices anymore. And sometimes people who work in a particular factory or whatever will have a notch loss because they're exposed to a particular loud sound at a particular frequency. There's even a study in Sweden correlating the notch loss with the factory sound in people who died of cancer. People who knew they were going to die willed their bodies or their ears to be tested, and it was then possible to correlate the measured loss in an individual with the sound to which he, and not she in this case, but he was exposed.
On the spontaneous emission, what's actually driving that? Is it the same air bundles that pick up the sound, get it and vibrating, and there's an active back and forth, or is it a different?
No, it's the same. It's the same bunch of hair cells. So the apparatus in our own cochlea, I showed you a diagram of it briefly. It's rather more complicated than the frog, which is why we use the frog. But in the mammal, there are 3 rows of so-called outer hair cells, 1 row of so-called inner hair cells, and then there's a gelatinous structure, the tectorial membrane, overlying that and serving as a mechanism of applying force to the tips of the hair bundles. These outer hair cells don't send significant information into the brain. They, in fact, are the amplifier, and they receive efferent control from the brain. So the brain can turn them up or down to control just how strong the amplification is. You do all of your hearing with this set of cells, the inner hair cells. But basically, the apparatus that I described, the hair bundle and so on, is the same in all of these. Yes. Yeah, so a long time ago, people came up with the Rene test. What he noticed was that you can usually hear a tuning fork, say, next to your ear, and you can take the same tuning fork and put its base on the temporal bone just behind the ear, and you can hear that very well. Sometimes there is damage to the apparatus that conducts sound into the cochlea, the eardrum, or particularly the bones of the middle ear. In that case, airborne sound doesn't go through very well because the bones, for example, are stuck together in otosclerosis. But the inside, the cochlea still works fine. So if you apply the tuning fork to the bone, you hear that very well. So the basic test, the Rene test, is just that you listen to a tuning fork until it's quite faint. Then you apply it to the bone. And if it gets much louder in that latter circumstance, it says you have a problem in the middle ear. And that's as much as problems can be, it's good because the middle ear can be readily repaired. You can throw all the bones away and put in Teflon. That what to be chosen? I wouldn't quite that far, but right. So some of the really good work you say is quite right. As all likely know, nervous signaling involves action. And action has a duration of about 1 millisecond. And there's a refractory period after which it can be repeated. So you can very briefly fire these at 1,000, like 5 seconds. You can sustain that, as you said, for 200 to 500. So you really can't signal on a one-to-one basis anything faster than that. But the one-to-one is important because what happens as you go to higher frequencies is that if you have a sine wave that's at, let's say, 2 kilohertz or something like that, an action potential can fire, say, here, and then again fire over here. And when you look at the phase of this, you find that there's phase information preserved even as you start firing every second or third or fourth of these waves. So in humans, phase information is preserved by this means up to 4 kilohertz. In owls, it's known to go up to 9 or 10 kilohertz. So the system can preserve phase, and that's very important for some of the ways we use sound. One of them is the localization of sound sources. So if there's a sound over there, you can point to where that chalk hit with a precision of 1 degree in azimuth. It's worse, it's 10 degrees vertically. But that comes about in part because if the sound is a relatively low frequency, as the wave moves past, it's at different phases at my 2 ears, right? So I get a compression here, and now a compression over there. And it's necessary to have this kind of phase locking and this kind of precision in order to get that to work. So what happens at higher frequencies is that we use entirely what's called pitch by place, namely a frequency that causes an oscillation here will excite this portion of the basilar membrane. The nerve fibers there are labeled lines corresponding in this case to say 10 kilohertz. So even though there's no phase encoding anymore, there's a unique one-to-one mapping between the incoming sound, the position of oscillation, and the nerve activity.
You mentioned briefly how the Brownian motion sound is suppressed. And I wonder
Well, no, I didn't actually say Brownian motion was suppressed. I think, in fact, it's very likely that we hear everything down to Brownian motion, and that is what sets the threshold at which we can hear it. So we're probably just getting Brownian motion, buffeting the hair bundles all the time. Anything significantly smaller than that, we don't hear. Now, there's a little bit more subtlety to it, which is, if you look at what Brownian motion does to individual hair bundles, it produces an oscillation and that is on the order of, this is 3 nanometers root mean square. And yet we can hear, as I said, signals down to about 0.3 nanometers, a tenth of that. And this comes about from the fact that a sinusoidal signal can be time averaged, right? So even though each cycle is producing this very small oscillation, if we time average over many hundreds of repetitions, we can dig this signal out of that amount of noise. And I should say, it was actually physicists, it was Thomas Gold, of all people, who really brought this idea to the fore. He realized that it was very hard to imagine that something like this could occur unless you had some sort of a resonant system, right? If you have a resonant system like the opera singer singing to the glass, it builds up a response over many cycles and you can get a signal that's bigger than the noise. But the ear shouldn't be resonant because it's overdamped. All of this, like all of biology, is underwater. So how can this be? And Gold's idea that was really seminal is that there must be an amplifier. There must be something that pumps energy in to overcome viscous dissipation in this overdamped environment.
Why do we typically use high frequency hearing?
Yeah, that we don't really know. This is very typical, as you say. Remember, the cells down here, the high frequency ones, are vibrating literally 20,000 times a second. So this hair bundle is going like mad. The ones here are vibrating 20 times a second. So these guys are getting 1,000 times the mechanical stimulus. Now, why exactly the stress might wear out molecules, I can't tell you. The other thing is the traveling wave, which carries sound energy into the cochlea, starts here. So every frequency causes some deformation here, even though the peak may be higher up. So these guys are in fact taking more of a beating as a result of that as well. But I can't give you a real molecular answer. I wish I could. We wonder what wears out and whether something can be done to protect it or repair it. Thank you very much.